Hi friends, so here we are going to look at theorem 7.17, which is about uniform convergence and differentiation. So here the theorem states that suppose sequence fn is a sequence of functions differentiable on closed interval a comma b and such that sequence fn of x naught converges for some point x naught on a comma b, then if sequence f dash of n converges uniformly on closed interval a comma b, then sequence fn converges uniformly on a closed interval a comma b to a function f, and also f dash of x equal to limit n tends to infinity f dash n of x where a less than or equal to x less than or equal to b. So here we have a sequence fn which is differentiable on closed interval a comma b, and also fn of sequence fn of x naught converges for some point x naught on a closed interval a comma b. Then we want to prove that sequence fn converges uniformly on a comma b to a function f, and also f dash of x equal to limit n tends to infinity f dash of n of x if sequence f dash of n converges uniformly on closed interval a comma b. So let us look into the proof. So let epsilon greater than 0 be given. Now we are going to choose a capital N such that n greater than or equal to n and m greater than or equal to n implies modulus fn of x naught minus fm of x naught less than epsilon by 2. So say this as equation 1, and modulus and the distance between the derivatives of, that is modulus f dash n of t minus f dash m of t less than epsilon by 2 into b minus a, where a less than or equal to t less than or equal to b. If we apply the mean value theorem to this function fn minus fm, where the mean value theorem states that suppose f is a continuous mapping of closed interval a comma b into r power k, and f is differentiable in open interval a comma b, then there exists a point x belong to a comma b such that modulus f of b minus f of a less than or equal to b minus a modulus f dash of x. So this is the mean value theorem. Then if we apply the mean value theorem, the above inequality shows that modulus fn of x minus fm of x minus fn of t minus fm of t then equal to modulus x minus t into modulus f dash n of t minus f dash m of t. Here by distributing the minus sign into the bracket, we get modulus of fn of x minus fm of x minus fn of t plus fm of t less than or equal to modulus x minus t into epsilon divided by 2 into b minus a, which is less than or equal to epsilon by 2. So say this as equation 3, as we already defined equation 1 and 2. Then here for any x and t on closed interval a comma b if n and m greater than or equal to n. So the inequality modulus fn of x minus fm of x less than or equal to modulus fn of x minus fm of x minus fn of x naught plus fm of x naught plus modulus fn of x naught minus fm of x naught x naught, which is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. This is got when we add and subtract fn of x naught and fm of x naught to the equation modulus fn of x minus fm of x. So by the so here we have x naught and t and x all lies between closed interval a comma b. So fn of x naught minus fm of x naught is also less than or equal to epsilon by 2. So equation by equation 1 and equation 3 we get modulus fn of x minus fm of x is less than epsilon, where a less than or equal to x less than or equal to b and nm greater than or equal to n. So the sequence fn converges uniformly on closed interval a comma b. Let f of x equal to limit n tends to infinity fn of x, where a less than or equal to x less than or equal to b. So now let us now fix a point x on closed interval a comma b, and now we can define phi of t and phi n of t for t in closed interval a comma b. So here phi n of t equal to fn of t minus fn of x divided by t minus x, and phi of t equal to f of t minus f of x minus t minus x. Sorry, divided by t minus x. Say this as equation 4. For any a less than or equal to t less than or equal to b and t not equal to x. So we want to show that f is differentiable. That is same as to show that limit of phi n of t where t tends to x exists. That is limit of t tends to x phi n of t equal to f dash of n of x, where n equal to 1, 2, 3, etc. And now say this as equation 5. Phi n of t converges uniformly in interval in closed interval a comma b except at t not equal to x. Then x is a limit point of closed interval a comma b. Then we can claim that the first inequality in equation 3 shows that modulus phi n of t minus phi m of t is less than or equal to epsilon divided by 2 into b minus a, where n and m greater than or equal to n. So that sequence phi n converges uniformly for t not equal to x. So since sequence fn converges to f, we conclude from equation 4, that is phi n of t and phi n of t and phi of t limit we get limit n tends to infinity phi n of t equal to phi of t. Say this as equation 6. Uniformly for a less than or equal to t less than or equal to b and t not equal to x. So now applying theorem 7.1, that is theorem 7.1 states that suppose fn converges to f uniformly on a set E in a metric space, then let x be a limit point of E, and suppose that limit t tends to x fn of t equal to an, then sequence an converges and limit t tends to x f of t equal to limit n tends to infinity an. That is here fn is a function from defined from E to R. So let x be a limit point of E, and suppose limit t tends to x fn converges to f uniformly, then this equation exists, that is limit t tends to x fn of t equal to an exists. Then limit n tends to infinity an x also exists. Then if both, that is limit n tends to infinity an and limit t tends to x f of t exist, both exist, then both will be equal. That is limit n tends to infinity an equal to limit t tends to x f of t, where n equal to 1, 2, 3, etc. So this is the theorem 7.11, and if the claim is true, then applying this theorem to sequence phi n in equation 5 and equation 6, we get limit t tends to x phi of t equal to limit n tends to infinity f dash n of x. So by applying limit to the definition of phi of t, that is limit t tends to x phi of t equal to limit t tends to x f of t minus f of x divided by t minus x. this will be equal to f dash of x. So this equation will be changing to f dash of x equal to limit n tends to infinity f dash n of x. So hence we get the part which we want. So hence the proof. That's all. I hope you understood. If there is any doubt, feel free to ask. Thank you.